This is Mrs. Palmer-Quay with the first video for Unit 5 on the skeletal system. In this video, I want to go over the basic functions of the skeletal system and some information on bone structure and development. There'll be a second videotape for this week that will go over specific bones and give you a list of which particular bones out of the 206 in the adult human body you need to be sure to know. So let's start with bone function. There are 5 different functions that bones perform for us. They support our body weight and give us some shape and structure to our bodies. They provide protection for internal organs. If we didn't have bones, our muscles would not be able to give us movement or locomotion. They have a very important role in producing blood cells of all types and serve as a mineral reserve because many of the mineral ions are very important for other bodily functions. Just to give you a little more specifics on this, and I apologize for the size of the font. I'm not sure why it shrunk this time. I even changed the type of font and it still took it down about 3 sizes. So we're going to have to just live with tiny type this time. But in the support function, I've just divided this again. These are the support functions. This is protection and then muscular movement. I already mentioned that our body shape comes from our bones, and we see that very clearly on the skull, especially if you see someone who is very thin, not much subcutaneous fat. You can see the skull really underneath the skin of their face. And then your pelvis and backbone and legs all work together to support your body weight. There's quite a bit of protection that comes from your skeletal system. We've mentioned the skull and the vertebrae. They provide protection for your central nervous system, your brain and your spinal cord. And I know you know that the ribs surround your heart and lungs and provide protection there. And the pelvis provides much protection for the abdominal cavity except for the straight-on frontal approach. If you think about it, your ribs come quite close to the top of your hips down your side. If you run your hand down your side, you can see that there really isn't very much space between the bottom of the ribs and the top of the hips. So from 3/4 of the way around your body, you're pretty well protected by your skeleton. And then the bones work in conjunction with the muscles to be levers or levers that amplify muscular action. There are 3 different classes of levers, and we have all 3 types in the human body. But the most common one is the 3rd class of lever, like we have with the biceps. So if we have just a little arm drawn here, and there's a hand sticking out, a few extra fingers, your biceps muscle will attach not at the elbow but just past the elbow on the forearm. And if it contracts, then your hand will also move. And a little bit of contraction here, a little tiny movement of contraction leads to a large amount of movement down at the end of your arm. That's the characteristic of a 3rd class lever, that a small change at the force here gives you a large change down at the end, and that's quite helpful for us with all the movement that we do with our bodies. The fancy name for the blood cell formation is hematopoiesis, and this occurs in the red bone marrow that is found inside our bones. It's found in many, many bones when we are young, but as adults it's found primarily in our skulls and the spongy bone, and we'll get to what spongy bone is in a few slides. But it's found in our skull, in our ribs, sternum, that's the breastbone, clavicles, the collarbone, vertebrae, and the hips. And if you are ever in a position to donate bone marrow to a family member or a friend who is undergoing treatment for cancer, they will stick a big needle into your pelvis and try to remove some of your red bone marrow to contribute to the patient's. So this is the preferred place if you are giving a bone marrow transplant. There are several different types of blood cells that are made in red bone marrow. Red blood cells, of course, and that's where the name comes from because the bone marrow has that characteristic red color because of hemoglobin. But also white blood cells that are very much involved in the immune system, and we have 5 different kinds of white blood cells that we'll be talking about as we move through this course. And then platelets, which we've already talked about, is something that's involved in clotting, blood clotting, and wound healing. Then finally, a mineral reserve is found in your bones. Bones are made up primarily of calcium phosphate with a little bit of calcium carbonate involved in there. And two hormones, calcitonin and parathyroid hormones, control the calcium levels in the blood and the bone. So when calcium levels in the blood get too high, calcitonin, and some people say you can remember it, tones down the level of calcium in the blood. It lays it down in the bones, and if the calcium level in the blood gets too low, parathyroid hormone releases the calcium from the bone. So these two hormones work together, and we'll be talking about them a little bit more in the endocrine system, but they are the ones in charge of moving calcium in and out of the bones. Calcium in the blood is helpful to maintain proper muscle contraction, including the heart muscle, and nerve impulses and blood clotting. So these are all pretty essential roles. And then several other minerals can also be found in the bones, magnesium, sodium, and potassium being the three big ones, so that this is a place that minerals are stored for use later, kind of a bank of minerals. Also, if you happen to get exposed to any minerals that perhaps are not particularly beneficial, they can end up in your bones as well. Things like radium or mercury, some of the heavy metals that we're concerned about as pollution in the environment, will end up in your bones. So bones can be classified by several different ways. You can see from this picture that there are quite a variety of sizes and shapes in the human bone collection, but there is similarity in how they are structured and how they develop. There are 4 classes of bones I want to be sure that everybody knows, and then there's 2 more on here just for fun. The first one are long bones, and this name is very obvious. These are bones that have more length than they have width. This includes, of course, the long bones of the upper arm, the humerus, and then the femur, the long bone of the thigh, but it also includes the long bones found in the fingers because they are longer, they are taller than they are wide. The second category of bones are short bones. These bones are roughly cube-ish in shape, about the same height and width. And this one example of some short bones are the many, many little bones that are found in your wrist and the palm of your hand. The third group of bones are flat bones, and these are pretty obvious. These are broad bones that are not very deep. Here is a bone from your skull, the parietal bone. This goes right across the middle of your skull. Your shoulder blade, your scapula is another common flat bone. Ribs are basically flat bones. They're more flat than they're round. And then the fourth category of bone that I want to make sure you know is the irregular bone. This is a bone that has an irregular shape. It often has many things sticking out, and we call these sticking out parts when we're talking about bones processes. So this vertebrae is an example of an irregular bone. Then 2 more types of bones that you will see are sesamoid bones, and these are bones that are completely encased by ligaments. So this is the kneecap here, and there are ligaments running over and around this whole bone. Interestingly, when babies are born, they don't have a kneecap. It develops as stress is put on that joint when they move from being just sort of quiet little lumps to actively crawling around. Because sesamoid bones, or because this kneecap in particular, develops because of stress, sometimes sesamoid bones are described as bones that other bones that develop because of stress. A key example of that would be a bone spur that can develop because of stress on a certain part of an anatomy because of a repetitive motion. So people develop bone spurs on parts of their fingers, their thumb, perhaps their heel, because of continually stressing that bone. And then the final category of bone are sutural bones, which are bones that are completely enclosed by sutures. So this is a little sutural bone running into the other bones of the skull, and all the way around it has this kind of a jagged edge that's known as a suture. The long bone sort of typifies what we think of when we say bone, and so we use this to point out some of the important parts of a bone. So for any long bone, as I said, your humerus or your femur or some of your phalanges, your finger bones, the ends of the bone are known as the epiphysis. So there's 2 epiphyses on this particular bone. And as it is positioned in the body, we have some directional terms. So the proximal epiphysis is the part that would be closest to the torso, the trunk of the body. And the distal epiphysis would be the part that was further away. So on this humerus, here the shoulder would be attached here on the proximal epiphysis, and down here we would get the bones of the lower arm, the radius, and the ulna. The part in the middle, the shaft, is known as the diaphysis. Around the outside of the bone, you have a very dense material, very strong, very thick, no holes in it. This is known as compact bone, and we'll get into more of this later. And then, especially on the epiphysis, sometimes moving down a little bit beyond that into the diaphysis, we have what is known as spongy bone, which looks like a sponge but is not soft like a sponge. It's still rigid material, but there are more air holes in it. Spongy bone has more air space because this allows the entire bone to be much lighter and does not require as many muscles to have us move around. On the bones that move, and all of our long bones are ones that will be part of movement, you have cartilage on either end. And so the general term for that is articular cartilage. It's hyaline cartilage. These are, articulation means movement, and so on both ends by the epiphysis you will have cartilage, because bone grating on bone is exceedingly painful, whereas cartilage provides a smooth surface for these 2 parts of the 2 bones to travel over each other when the joint moves. Here's just a close-up of the very, very edge of the epiphysis here. You can see we have the thick, compact bone on the outside. It's also known as cortical bone. And then you have the spongy bone, or the cancellous bone, into the center. And then over the outside we have the articular cartilage. This particular diagram comes from the diaphysis, and we see that the very, very center of the bone is empty. This is known as the medullary cavity, and in there it's not completely empty. It is full of something. It is full of this yellow stuff in adults, which is known as yellow marrow, or yellow marrow. It is a last-ditch fat storage place. If you are starving and you have exhausted all your subcutaneous fat, there is a little bit of fat stored in your bones to try to get you, to survive another day until situations improve. Biologists that are doing research on animal populations that experience death in the wintertime are often looking at, are there any fat stores left in the bones? Is there any yellow marrow left? Because this would be an indication when they're finding a dead animal, is it dying because of starvation or of some other factor. Around the outside of these bones is periosteum, which is a connective tissue layer. And from the periosteum, you have a direct connection, a contiguous connection to the various tendons and ligaments that help hold the bones together and attach the muscles to the bones. Also in the periosteum, you have the blood vessels coming in, but they go through into the bone through various holes and grooves. So we actually have blood vessels through the middle of the compact and spongy bone, which we'll get to in a minute. So let's look at some microscopic structure of the bones. As I started off saying, that bone is a connective tissue, which means you have cells plus a great deal of extracellular matrix. The mature bone cells are called osteocytes, and you should see a pattern here. We have the periosteum, osteocyte, osteo is referring to the bones. The extracellular matrix in bones is the combination of collagen and these mineral salts. We mentioned calcium phosphate and calcium carbonate. Collagen gives the bone strength and resilience, but it is very bendy. Collagen is found in tendons. We know it is very, very strong. It is that thicker fiber that is produced by the fibroblasts and the cells, the bone cells, which you will go on in another slide. I'll show you the word osteoblasts. So fibroblasts developed into osteoblasts, bone cells, and they produce collagen. So if we just had collagen in our bones, they would be strong, but they would be much too flexible. So the mineral salts make the bones hard and unbending and allow the bones to support however much you happen to be weighing, allow your muscles to give something strong to pull against. So we need both of them to make the bones. Here is a slide of bone cells. And in the center, this is again compact bone, you can see that we have these circular structures. And these are known as osteons, again that osteo prefix. They are made up of individual osteocytes, bone cells, which are these little dark spots here. And if this was a large enough magnification, you would see that around each of these cells you have that empty chamber of lacunae that is typical in many of the connective tissue cells. So the osteocytes, these mature bone cells found inside the extracellular matrix, can be seen as these little dots. These darker sections in the middle are actually blood vessels, or often blood vessels and nerves. They go longitudinally through the compact bone structure, and they also go transversely. So here we've got one that was cut in half as the slide was prepared. So this is a blood vessel connecting, sort of a side tunnel connecting these two vertical blood vessels. This section is called the central canal, or the Haversian canal. And the whole system sometimes is called a Haversian system. So the spaces in between the dark osteocytes is the extracellular matrix. It's where the mineral salts are laid down. It is the hard part. And you can see how they all sort of come very close together. They are running into each other. The extracellular matrix is filling in all the space in the compact bone. So here is a diagram to show what you see in that previous slide. Here's the osteon, this circular structure where you've got several rings of osteocytes, and they actually kind of look like millipedes. You have sort of a central cell, but they have these long cytoplasmic processes, again things that stick out, that allow them to connect and communicate with the other osteocytes all throughout the extracellular matrix. You can sort of see it on some of the diagrams here, these long processes. So we have the blood vessels and the nerves running up and down and across, connecting, providing nutrients, transferring signaling information. There are quite a few nerves in your bones, which is why it hurts so much when you break them. And there are quite a few blood vessels in your bones, which also explains why you end up with very badly bruised areas when you have broken a bone. I forgot to mention that these cytoplasmic processes are called caniculi. They've got a plural here, caniculus, and that's just their particular name. So then moving to spongy bone, the arrangement of the osteon does not happen around a central canal. The nerves and the blood vessels, the nutrients and the information they provide have to be diffusing into this central area, the air-filled, spongy-looking bone tissue. And so we have a close-up down here that just shows how you still do have the osteocytes and this concentric circle arrangement and the caniculi going out from one cell to the other, but you don't have the same kind of nerve and central blood vessel situation. So this gives you just sort of an overview of the diagram of these two types of bone tissue. The outer section, again, is the compact bone running around the outside of your bones, and then the spongy bone underneath that. Here are some pictures of actual bone where you can see here we've got a cross section of one of the long bones, and so you can see here we've got all of this thick compact bone, no air spaces, and then the spongy bone in the middle. So this bone obviously is very strong. The compact bone provides a lot of resistance for weight-bearing activities, but when you've got movement in different directions, the spongy bone in the middle helps provide stress that's coming at you from many different ways. So there are advantages to having these sort of cross trusses like you would see in a bridge in the middle of your bones, along with this very, very solid compact bone around the outside. Here we have a bone from the skull, and you see again you have the same type of situation. Compact bone on the outside, spongy bone in the middle. Here we have a close-up of the epiphysis of either a femur or a humerus, And you can see that there's quite a bit of spongy bone in this, that there's not as much compact bone around the outside, but a lot of spongy bone. And if you just think about in a rotating joint as you have in your shoulder or your hip, you would be having stress coming at that bone from many directions. And so having a large amount of spongy bone would be advantageous because it would be able to catch and deal with the stress coming at from any angle. Here you see the big open medullary cavity that is found in the center of the long bones, and again, this is where the yellow marrow is found in adults. This information is not required on bone development and growth, but I'm providing it to you just for your own depth of knowledge. The skeletal system itself begins to develop very early on in prenatal development, usually about week 3 or week 4. You start seeing the beginnings of things happening that will become our skeletal system. And there are 2 ways that bone is made. Ossification is the scientific word for laying down of bone. We have bones that develop from intramembranous situations, or between membranes. And these are for bones that will end up being broad and flat, like your skull bones. Show sheet-like layers of connective tissue, have the mineral matrix laid down in them. The fibroblasts, which are part of connective tissue, the cell of connective tissue, specialize to become osteoblasts and start producing the mineral matrix. And you have the flatter bones developing. But most of your bones come from endochondral ossification. And if you see this chondral word, if you remember, that is referring to cartilage. We saw that the chondrocytes, the specific cells that made cartilage in our connective tissue video. And so in this situation, the bones begin as hyaline cartilage, as models of the future bones. They are in the shape of the future bones, and then the cartilage is slowly replaced by the hard bone matrix, by the osteoblasts. And most of the bones of the skeleton do develop as endochondral bones being ossified. So this is a little picture of the process. You don't, again, need to know this. It's just for your own information. But you start off here with your model made out of cartilage, and then the fibroblasts get specialized into osteoblasts and begin laying down the bone matrix in the central part of this cartilage model. Gets to a point where you see we've got some openness happening. The medullary cavity begins to develop. We have some blood vessels coming in, probably some central canals are being formed along here. If bone needs to be removed in this process as things are modeled and shaped, just like we talked about how cell death was important in taking a hand web into a hand with 5 fingers, we have osteoclasts. So you've got these 2 osteoblasts lay down bone, and osteoclasts take it away. And then osteocytes are the mature cells sitting there in their extracellular matrix of bone tissue. So as the central part of the bone strengthens and turns into bone instead of cartilage, then you start to see some ossification, some bone developing on the epiphyses, so on either end. So in the middle first and then on either end. And eventually you'll get to a point where you have bone here in the center, and then you have bone on the epiphyses, and there is this layer of cartilage in between. Epiphyseal disc or epiphyseal plate, and this is where growth is going to continue because, of course, as you know, a baby is much, much smaller than an adult, and there is quite a bit of lengthening that has to happen in the bones over time. And so bones, though, are hard. They don't stretch particularly. They need to continue to grow because more cells are being added to it. So the growth happens at the epiphyseal plate or epiphyseal disc at the end of the bones. So here are some x-rays. You can see the situation. This is a child's x-ray. This is the knee, and it looks like there's a crack running right down the middle of the bone. X-rays will take a picture of bone. Bone tissue is much harder. It won't let the X-ray ray through in order to hit the photographic plate, and so it shows up as a white patch where there's no rays coming through, whereas a section where X-rays can go through, like here with the soft tissue of the muscle, you can see that it has sort of a grayish look to it. And so instead of, this isn't a crack per se here on the epiphyseal plate, but it is a space that is cartilage. And so cartilage is being turned into bone on this side of the plate, and new cartilage is continually being made on this side of the plate, so the entire bone is growing in this direction. And since there's another growth plate on the other end of the bone, it is also moving that way. So the end result is that the bone is growing longer. These growth plates are visible as long as someone is still actively growing. So until their teenage years, you can look at an X-ray and see that this person is still in their growth stage. They haven't reached their final height or their final length of their fingers or whatever. Over here we have the same part of the body, a knee, but from an adult, and you don't see a gap in the bones anymore. There's no growth plate visible. Sometimes you can just see a very, very faint line where it used to be, like right here. It looks like there's a little bit of it. But it has closed up. It is now all bone. There is no cartilage in between. There's no more growth possible. So this is one thing that forensic anthropologists look at when they're trying to determine the age of a skeleton. They look to see what is the condition of the epiphyseal plate. Can't say that today. And it'll give them some indication about how old this skeleton, the person that belonged to the skeleton, might have been, based on whether they were still actively growing or have finished growing. There are several things that impact on your bone development and growth. I'm sure you are aware of the importance of vitamin D. Your nutrition has an impact on how well your bones grow. Rickets is a condition that developed during the Industrial Revolution, when so many people in the cities were living in neighborhoods where the houses were so close together, the sun never shone, and they were working very long hours. And it led to weak bones, and then the weight of the body would cause deformities, so the bones would be in an incorrect shape. Bow-legged, women were not able to bear children because their pelvis had been deformed. It was a serious problem, and was in part solved because vitamin D was added then as a nutritional supplement to milk to try to make sure that everybody got enough vitamin D. Another factor about lack of vitamin D is just there's not enough calcium put in the bones to begin with. That's what osteomalacia is. And so the cartilage dominates, and again you've got bones that are too flexible. They're too weak because they don't have enough bone matrix laid down. Several other nutrients are involved in bone growth. I'm sure you're aware that calcium works with vitamin D, but also vitamin A and vitamin C are part of this whole development package. Growth hormone controls how long your bones are, or how long the epiphyseal cartilage stays active. And so if growth hormone shuts off too soon, or it's insufficient in its quantity, someone can end up being too short, experiencing dwarfism, or if it continues past the point that it would normally stop, you have someone who experiences gigantism or acromegaly. If you've seen the Princess Bride, the actor Andre the Giant suffered from acromegaly and actually died from repercussions of it because he did not choose to have any kind of treatment to try to stop the excess production of growth hormone. Sex hormones at puberty also start the ossification of the epiphyseal plates. So when puberty hits, you're getting near the end of your active growing time. And then physical stress, specifically weight-bearing exercise, will actually strengthen and thicken bones, or the lack of weight-bearing exercise will encourage the osteoclasts to dominate and to thin out the bones. This is why astronauts living on the International Space Station spend a good portion of their day doing weight-bearing exercises, stressing their body to try to keep the calcium in their bones. They are not entirely successful, but they do manage to return home in much better shape than some of the earlier long-term astronauts who could barely stand up when they got back to Earth's gravity because of the loss of calcium from the bones. This is why exercise for just in general, doing something that allows you to carry weight will help strengthen your bones, because the stress on the bones encourages the osteoblasts to develop and to lay down more calcium and strengthen and thicken bones. So that's your quick overview of these parts of the skeletal system. Watch for the second video this week talking about particular bones.